The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Awesome. Okay, so today we're going to continue on with some of the design patterns they started talking about last week. So to recap, there are really 4 common steps to taking a program and then parallelizing it. Often you're starting off with a program that's designed or written in a sequential manner. And what you want to do is find the tasks in the program. And these are sort of independent work pieces that you're going to be able to decompose from your sequential code. You're going to group the tasks together into threads or processes. And then you'll essentially map each one of these threads or processes down to the actual hardware. And that will get you, eventually, when these programs run, the concurrency and the performance speedups that you want. Okay. So as a reminder of what I talked about last week in terms of finding the task or finding the concurrency, you start off with an application. You come up with its block-level diagram. And from that, you sort of try to understand where the time is spent in the computation and what are some typical patterns for how the computation is carried out. So we talked about task decomposition, or sort of independent tasks or tasks that might be different that the application is carrying out. So in the MPEG encoder, we looked at decoding the motion vectors for temporal compression versus spatial compression that does sort of substantially different work. We talked about data decomposition. So if you're doing a process, so if you have some work that's really consuming a large chunk of data, and you realize that it's applying the same kind of work to each of those data pieces, then you can partition your data into smaller subsets and apply the same kind of apply the same function over and over again. Okay. So in the motion compensation phase, that's one example where you can replicate the function and split up the data stream in different ways and have these tasks proceed in parallel. So it's data decomposition. And then we talked a little bit about sort of making a case for pipeline decomposition. So you have data assembly line or producer-consumer chains, and you essentially want to recognize those in your computation and make it so that you can exploit them eventually when you're doing your mapping down to actual hardware. But what does it mean for 2 tasks to actually be concurrent? And how do you know that you can safely actually run 2 tasks in parallel? So this is something I crudely went over last time. So to make it more concrete, highlighting Bernstein's condition, which says that given 2 tasks, if the input set to one task is different from or does not intersect with the input set to with the output set of another, and vice versa, and neither task sort of updates the same data structures in memory, then there's really no dependency issues between them, and you can run them safely in parallel. So tasks T1 and T2, if all the data that's consumed by T1, so all the data elements that are read by T1 are different from the ones that are read by T2, then you have, if T2 is running in parallel, there's really no problem with T1 because it's updating an orthogonal data set. Similarly, for T2 and T1, any outputs are different. So as an example, let's say you have 2 tasks. And in T1, you're doing some basic statements. Now, these could be essentially more coarse-grained. There could be a lot more computation in here. I've just simplified it for the illustration. So you have task A equals x plus y, and task 2 does b equals x plus z. So if we look at the read set for T1, these are all the variables or data structures or addresses that are read by the first task. So that's x and y here. And all the data that's written or produced by T1. So here we're just producing one data value, and that's going into location A. Similarly, we can come up with the read set and write set for T2. And so that's shown on here. So we have task T2 has x plus z in its read set, and it produces one data value B. And if we take the intersection of the read and write sets for the different tasks, then they're empty. I read something completely different than what's produced in this task. Vice versa, and they write to 2 completely different memory locations. So I can essentially parallelize these or run these 2 tasks in parallel. So you can extend this in this analysis, and compilers can actually use this condition to determine when two tasks can be parallelized if you're doing automatic parallelization, and you'll probably hear more about these later on. And so what I focused on last time were the finding concurrency patterns. And I had identified sort of 4 design spaces based on the work that's done, that's outlined in the book by Matson, Sanders, and Massengill. And so starting with 2 large sort of concepts. The first helps you figure out how you're going to actually express your algorithm. So first you find your concurrency, and then you organize in some way. And so we're going to talk about that in more detail. And then once you've organized your tasks in some way that actually expresses your overall computation, you need some software construction utilities or data structures or mechanisms for actually orchestrating computation, for which they've also abstracted out some common patterns. And so I'll briefly talk about these as well. And so in the algorithm expression side, these are essentially conceptualization steps that help you abstract out your problem, and you may in fact think about your algorithm expression in different ways to expose different kinds of concurrency, or to be able to explore different ways of mapping the concurrency to hardware. In software construction, it's more about actual engineering and implementation. So here you're actually thinking about what are the data structures look like? What is the communication patterns I'm going to look like? Am I going to use things like MPI or OpenMP? What does that help me with in terms of doing my implementation? So given collection of concurrent tasks, so you've done your first step in your 4 design patterns, what is your next step? And that's really mapping those tasks that you've identified down to some sort of execution units. So threads are very common. This is essentially what we've been using on Cell. We take our computation, we wrap it into SPE threads, and then we can execute those at runtime. So some things to keep in mind, although you shouldn't over-constrain yourself in terms of these considerations. What is the magnitude of your parallelism that you're going to get? Do you want hundreds or thousands of threads, or do you want something on the order of tens? And this is because you don't want to overwhelm the intended system that you're going to run on. So we talked about yesterday on Cell processor, if you're creating a lot more than 6 threads, then you can create problems, or you essentially don't get extra parallelism because each thread is running to completion on each SPE, and context switch overhead is extremely high. So you don't want to spend too much engineering cost to come up with an algorithm implementation that's massively scalable to hundreds or thousands of threads when you can't actually exploit it. But that doesn't mean that you should over-constrain your implementation to where if now I want to take your code and run it on a different machine, I essentially have to redesign or re-engineer the complete process. So you want to avoid tendencies to over-constrain the implementation, and you want to leave your code in a way that's malleable so that you can easily make changes to sort of factor in new platforms that you want to run on, or new machine architecture features that you might want to exploit. So there are 3 major organization principles I'm going to talk about. And none of these should be sort of foreign to you at this point, because we've talked about them in different ways, either in the recitations or in previous lectures. And it's really, what is it that determines sort of the algorithm structure based on the set of tasks that you're actually carrying out in your computation? And so there's the principle that says organize things by tasks. I'm going to talk through that. And then there's a principle that says, well, organize things by how you're doing the data decomposition. So in this case, how you're actually distributing the data, or how the data is laid out in memory, or how you're partitioning the data to actually compute on it, dictates how you should actually organize your actual computation. And then there's organized by flow of data. And this is something you'll hear about more in the next lecture, where we're talking about stream it. But in this pattern, if there are specific sort of computations that take advantage of high bandwidth flow of data between computations, you might want to exploit that for concurrency, and we'll talk about that as well. Okay, so sort of a design diagram for how can you actually go through each process. So you can ask yourself a set of questions. If I want to organize things by task, then there are essentially two main clusters, or two main patterns. If the code is recursive, then you essentially want to apply a divide and conquer pattern, or divide and conquer organization. If it's not recursive, then you essentially want to do task parallelism. So in task parallelism, these, I've listed 2 examples here, but really any of the things we've talked about in the past fit. Ray computation, the ray tracing. So here you're shooting rays through a scene to try to determine how to render it, and really each ray is a separate and independent computation step. In molecular dynamics, you're trying to determine the non-bonded force calculations. There are some dependencies, but really you can do each calculation for one molecule or for one atom independent of any other. And then there's sort of the global dependence of having to update or communicate across all those molecules to sort of reflect new positions in the system. So the common factors here are your tasks are associated within with iterations of a loop, and you can distribute the, each process. Each processor can do a different iteration of the loop. And often you know sort of what the tasks are before you actually start your computation, although in some cases, like in ray tracing, you might generate more and more threads as you go along, or more computation, because as the ray is shooting off, you're sort of calculating new things that are new reflections, and that creates a sort of extra work. But largely, you have these independent tasks that you can encapsulate in threads, and you run them. And this is sort of might appear subtle, but there are algorithm classes where not all tasks essentially need to complete for you to arrive at a solution. In some cases, you might convert to an acceptable solution, and you don't actually need to go through and exercise all the computation that's outstanding for you to say the program is done. So there will be a tricky issue. I'll revisit this just briefly later on, is how do you determine if your program is actually terminated or has completed? And divide and conquer, this is really for recursive programs. You can think of a well-known sorting algorithm, merge sort, that classically fits into this kind of picture, where you have some really large array of data you want to sort. You keep subdividing into smaller and smaller chunks until you can do local reorderings, and then you start merging things together. So this gives you sort of a way to take a problem, divide it into subproblems, and then you can split the data at some point, and then you join it back together, you merge it. You might see things like fork and merge, or fork and join used instead of split and join. I've used this terminology to sort of meld well with some of the concepts we use in StreamIt that you'll see in the next lecture. And so in these kinds of programs, it's not always the case that each subproblem will have essentially the same amount of work to do. You might need more dynamic load balancing, because each subproblem, how you distribute the data might lead you to do more work in one problem than in the other. So as opposed to some of the other mechanisms where static load balancing will work really well, and to remind you, static load balancing essentially says you have some work, you assign it to each of the processors, and you're going to be relatively happy with how each processor's sort of utilization is going to be over time. Nobody's going to be too overwhelmed with the amount of work they have to do. In this case, you might end up with needing some things for dynamic load balancing that says, I'm unhappy with the work performance or utilization. Some processors are more idle than the others, so you might want to essentially redistribute things. So we'll talk about, how does this concept of a divide and conquer parallelization pattern work into the actual implementation? How do I actually implement a divide and conquer organization? The next organization is organized by data. So here you have some computation. Not sure why it's flickering.
Check your VGA cables are in good.
Yeah, screw it too. Okay. So in the organized by data, you essentially want to apply this if you have a lot of computation that's using a shared global data structure, or that's going to update a central data structure. So in molecular dynamics, for example, you have a huge array that records the position of each of the molecules. And while you can do the force calculations independently, eventually everybody or all the parallel tasks have to communicate with the central data structure and say, here are the new locations for all the molecules. And so that has to go into a central repository. And there are different kinds of sort of decompositions within this organization. If your data structure is recursive, so a linked list or a tree or a graph, then you can apply the recursive data pattern. If it's not, if it's linear, like an array or a vector, then you apply geometric decomposition. And you've essentially seen geometric decomposition. These were some of the labs that you've already done. And so the example from yesterday's recitation, you're doing an n-body simulation in terms of who's gravitating towards who. You're calculating the forces between pairs of objects. And depending on the force that each object feels, you calculate a new motion vector. And you use that to update the position of each body in your, say, galaxy that you're simulating. And so what we talked about yesterday was, given an array of positions, each processor gets a sub-chunk of that position array, and it knows how to calculate sort of locally based on that. And then you might also communicate local chunks to do more scalable computations. In the recursive data structure are a little bit more tricky. So at face value, you might think that there's really no kind of parallelism you can get out of a recursive data structure. So if you're iterating over a list and you want to get the sum, well, I just need to go through the list. Can I really parallelize that? There are, however, opportunities where you can reshape the operations or reshape the computation in a way that exposes concurrency. And often what this comes down to is you're going to do more work, but it's OK because you're going to finish faster. So this kind of work concurrency trade-off, I'm going to illustrate with an example. So in this application, we have some graph. And for each node in the graph, we want to know what is its root. So this works well when you have a forest where not all the graphs are connected. And given a node, you want to know who's the root of this graph. So what we can do is essentially have more concurrency by changing the way we actually think about the algorithm. So rather than starting with each node and then in a directed graph following its successor, so this is essentially order n, because for each node we have to follow n links, we can think about it slightly differently. So what if, rather than finding the successor and then finding that successor's successor, at each computational step, we start with a node and we say, who's your successor's successor? So we can converge in this example in 3 steps. So from 5 to 6, we can say, who's this successor? So who's the successor of 5? And that would be 2. And similarly, you can do that for 7 and so on. And so you keep asking the question. So you can distribute all these data structures, repeatedly ask these questions out of all these n nodes, and it leads you to an order log n solution versus an order n solution. But what have I done in each step? Well, I've actually created myself I've sort of increased the amount of work that I'm doing by order n. Wait, is that right? Right, yes. Because I've essentially, for each node, I'm doing n queries. Who's your successor's successor? Whereas in the sequential case, I just need to do it once for each node, and that works really well. So most strategies based on this pattern of actually decomposing your computation according to the recursive pattern leads you to doing much more work, or some increase in the amount of work. But you get this back because you can decrease your execution. And so this is a good trade-off that you might want to consider.
Is it versus order n with sequential?
Yeah, this is a typo.
Okay.
Yeah. So organized by flow or organized by flow of data. And this is essentially the pipeline model. And we talked about this again in some of the recitations in terms of SPE to SPE communication. Or do you want to organize based on event-based mechanism? So what these really come down to is, well, how regular is the flow of data in your application? If you have regular, let's say, one-way flow through stable computation path, so I've set up my sort of algorithm structure, data is flowing through it at a regular rate, the computation graph isn't changing very much, then I can essentially pipeline things really well. And this could be a linear chain of computation, or it could be sort of nonlinear. It could be branches, in the graph. And I can use that in a way to exploit pipeline parallelism. If I don't have sort of this nice regular structure, there could be events that are created at runtime. So for example, you're a car wash attendant and a new car comes in, so you have to find a garage for it to assign to it and then trigger on the car wash machine. So there are dynamic threads that are created based on sensory input that comes in, then you might want to use an event-based coordination. You have irregular computation. Computation might vary based on the data that comes into your system. And you might have unpredictable data flow. So in the pipeline model, the things to consider is the pipeline throughput versus the pipeline latency. So the amount of concurrency in a pipeline is really limited by the number of stages. This is nothing new. You've seen this, for example, in superscalar pipelines. And just as in this case, as in the case of an architecture pipeline, the amount of time it takes you to fill the pipeline and the amount of time it takes you to drain the pipeline can essentially limit your parallelism. So you want those to be really small compared to the actual computation that you spend in your pipeline. And the performance metric is usually the throughput. How much data can you pump through your pipeline per unit time? So in video encoding, it's the frames per second that you can produce. And the pipeline latency, though, is important, especially in real-time application where you need a result every 10 milliseconds. Your pacemaker, for example, has to produce a beep or a signal to your heart at specific rates. So you need to consider what is your pipeline throughput versus your pipeline latency, and that can actually determine how many stages you might want to actually decompose or organize your application in. And in the event-based coordination, these are interactions of tasks over unpredictable intervals, and you're more prone to sort of deadlocks in these applications because you might have cyclic dependencies where one event can't proceed until it gets data from another event, but it can't proceed until it gets data from another event. And you can create sort of these complex interactions that often lead to deadlock. So you have to sort of be very careful in structuring things together so you don't end up with feedback loops that block computation progress. So given sort of these three organizational structures that say, I can organize my computation by tasks or by the flow of data or by sort of the pipeline nature of the computation, what are the supporting structures? How do I actually implement these? And so there are many different supporting structures. I've identified sort of four that occur most often in literature and in books and common terminology that's used. And so those are SPMD, loop parallelism, the master worker pattern, and the fork join pattern. In the SPMD pattern, you're talking about a single program, multiple data concept. And so here you just have one program, you write it once, and then you assign it to each of your processors to run. So it's the same program, it just runs on different machines. Now, each program or each instance of the code can have different control flow that it takes. So just because they're running the same program doesn't mean the computation is happening in lockstep. That would be a sort of a SIMD or a vector-like computation. In this model, you can actually take independent control flow. It could be different behavior in each instance of the code, but you're running the same code everywhere. So this is slightly different, for example, from what you've seen on Cell, where you have the PPE thread that creates SPE threads. Sometimes the SPE threads are the same, but it's not always the case that the PPE thread and the SPE threads are the same. So in the SPMD model, there are really 5 steps that you do. You initialize sort of your computation in the world of sort of code instances that you're going to run. And for each one, you obtain a unique identifier, and this usually helps in being able to determine who needs to communicate with who or ordering dependencies. And you run the same program on each processor. And what you need to do in this case is also distribute your data between each of the different instances of your code. And then once each program is running, it's computing on its data. Eventually, you need to finalize in some way. And so that might mean doing a reduction to communicate all the data to one processor to actually output the value. And so we saw an SPMD example for the numerical integration for calculating pi. And if you remember, so we had this very simple C loop, and we showed the MPI implementation of the C loop. And so in this code, what we're doing is we're trying to determine different intervals. And for each interval, we're going to calculate a value. And then in the MPI program, we're essentially deciding how big an interval each process should run. So it's the same program. It runs on every single machine or every single processor. And each processor determines, based on its ID, how much which interval of the actual integration to do. And so in this model, we're distributing work relatively evenly. Each processor is doing a specific chunk that starts at, say, some index I, and if I have 10 processors, I'm doing 100 steps, then you're doing I plus 10, I plus 20, and so on. But I can do a different distribution. So the first is a block distribution. I can do something called a cyclic distribution. So in the cyclic distribution, I distribute work sort of in a round-robin fashion or some other mechanism. So here, each processor, sorry, I screwed up. In the block distribution, I start an interval I, and I go, sorry. So each processor gets one entire slice here. So I start here and I go through to completion. I start here and go through to completion. In the cyclic distribution, I might do smaller slices of each one of those intervals. And so I grayed out the components for the block distribution and just showed you that for contrast here. There are some challenges in the SPMD model, and that is how do you actually split your data correctly? You have to distribute your data in a way that doesn't increase contention on your memory system, where each actual processor that's assigned computation has data locally to actually operate on. And you want to achieve an even work distribution. Do you need a dynamic load balancing scheme, or can you use an alternative pattern if that's not suitable? So the second pattern, as opposed to the SPMD pattern, is the loop parallelism pattern. And in this case, this is best suited when you actually have a programming model or a program that you can't really change the whole lot, or that you don't really want to change the whole lot. Or you have a programming model that allows you to sort of identify loops that take up most of the computation and then insert annotations or some ways to automatically parallelize those loops. So we saw in the OpenMP example, you have some loop, you can insert these pragmas that say this loop is parallel, and the compiler and the runtime system can automatically partition this loop into smaller chunks, and then each chunk can compute in parallel. And you might apply this scheme in different ways depending on how well you understand your code. Are you running on a shared memory machine? You can't afford to do a whole lot of restructuring. Communication costs might be really expensive. In the master worker pattern, this is really starting to get closer to what we've done with the cell recitations and the cell labs. You have some world of independent tasks, and the master is essentially running and distributing each of these tasks to different processors. So in this case, you get several advantages that you can leverage. If each of your tasks are vary in nature, and they might finish at different times or they require different kinds of resources, you can use this model to sort of view your machine as sort of a non-symmetric processor. Not everybody is the same, and you can use this model really well for that. So you can distribute these, and then you can do dynamic load balancing, because as processors, as workers finish, you can ship them more and more data. So it has some particularly relevant properties for heterogeneous computations, but it's also really good for when you have a whole lot of parallelism in your application. So something called embarrassingly parallel problems. So ray tracing, molecular dynamics, a lot of scientific applications have these massive levels of parallelism, and you can use this essentially work queue-based mechanism that says I have all these tasks and I'll just dispatch them to workers and compute. And as I pointed out earlier, when do you define your entire computation to have completed? Sometimes you're computing a result until you've reached some result, and often you're willing to accept a result within some range of error. And you might have some more threads that are still in flight. Do you terminate your computation then or not? What are some issues with synchronization? If you have so many threads that are running together, does the communication between them to send out these control messages, say I'm done, start to overwhelm you? In the fork join pattern, this is really not conceptually too different in my mind from the master worker model, and also very relevant to what we've done with cell. you have tasks. The main difference might be that you have tasks that are dynamically created. So in the embarrassingly parallel case, you actually know the world of all your potential tasks that you're going to run in parallel. In the fork join model, some new computation might come up as a result of, say, an event-based mechanism. So tasks might be created dynamically and then later terminated, or they might complete, and so new ones come up as a result.
You can almost think like you are forking task forking set to map the number of processes in the work queue model, and then keep assigning tasks to that. Whereas fork join model, you just keep forking as work shows up. That might not be completely matched to number of processes available. So if you have 6 SPs, you have 6 things forked, and they will keep accepting work or just busy waiting for work. Whereas here, as work comes, you will just fork them out.
So the process that's creating all these threads, or that's doing all the forking, is often known as the parent, and the tasks that are generated are the children. And eventually, essentially, the parent can't continue or can't resume until its children have sort of completed or have reached the join point. And so those are really some of the models that we've seen already in a lot of cases in the recitations and labs for how you run your computations. And some of you have already discovered these and actually thinking about how your project should be sort of parallelized for your actual cell demos. Some of the other things I'm just going to talk about are communication patterns. So 2 lectures ago, you saw, for example, that you have point-to-point communication, or you have broadcast communication. So in point-to-point communication, you have 2 tasks that need to communicate, and they can send explicit messages to each other. These could be control messages that say, I'm done, or I'm waiting for data. Or they could be data messages that actually ships you a particular data element that you might need. And again, we've seen this with cell. Broadcast says, I have some result that everybody needs, and so I send that out to everybody by some mechanism. There is no real broadcast mechanism on cell. Concept I'm going to talk about, though, is the reduction mechanism, which really is the inverse of the broadcast. So in the broadcast, I have a data element I need to send to everybody else. In the reduction, all of you have data that I need, or all of us have data that somebody else needs. So what we need to do is collectively bring that data together or group it together and generate an end result. So a simple example of a reduction, you have some array of elements that you want to add together. And sort of the result of the collective operation is the end sum. So you have an array of 4 elements, A0, A1, A2, and A3. And you can do a serial reduction. I can take A0 and add it to A1, and that gives me a result. And then I can take A2 and add that to it. And I can take A3 and add that to it. And so at the end, I've sort of calculated the sum from A0 to A3. So this is essentially the serial reduction applies when your operation isn't associative. So the addition is associative. So in this case, I can actually do something more intelligent. I'm going to show, and I think we talked about that last time. I'm going to show you some more examples. And often, sort of the end result follows a broadcast. It says, here's the end result. Who are all the people that need it? I'll sort of broadcast that out so that everybody has the result. If your operation isn't associative, then you're essentially limited to a serial process. And so that's not very good from a performance standpoint. Some of the tricks you can apply for actually getting performance out of your reduction is to go to a tree-based reduction model. So this might be very obvious. Rather than doing A0 and A1 and then adding A2 to that result, I can do A0 and A1 together. In parallel, I can do A2 and A3. And then I can get those results and add them together. So rather than doing n steps, I can do log n steps. So this is particularly attractive when only one task needs the result. So in the MPI program, when we're doing the integration to calculate pi, one processor needs to print out that value of pi. But if you have a computation where more than one process actually needs the result of reduction, there's actually a better mechanism you can use that's sort of a better alternative to the tree-based reduction followed by a broadcast. So you can do a recursive doubling reduction. So this is so at the end here, every process will have the result of the reduction without having done a broadcast. So we can start off as with the tree base and add up A0 and A1 together. But what we do is, for each process that has a value, we sort of do a local exchange. So from here, we communicate the value to here, and from here, we communicate the value to here. And so now these two processors that had the value independently now both have a local sum, A0 to A1. And similarly, we can sort of make the similar symmetric computation on the other side. And now we can communicate data from these two processors here to come up with the end. Yeah. It was there. I must have lost in the animation. So you actually do that the other way as well, so that you have the sum A0 to A3 on all the different processors. Sorry about the lost animation. OK, so this is better than the tree-based approach with a broadcast because you end up with the local result of the reduction. And rather than doing the broadcast following the tree-based reduction, which takes n steps, you end up with an order n. Everybody has a result in order n versus an order 2n process for the tree-based plus broadcast. Amir?
On the cell processor, but not in general.
Not in general. It depends on sort of the architectural mechanism that you have for your network. If you actually do need to sort of, if you have a broadcast mechanism that has a bus-based architecture where you can deposit a local value, everybody can poll that value, then yeah, it can be more efficient. Or in optical networks, you can broadcast the data and everybody can just fuse it out. Okay. So summarizing all the different patterns. So here, these are the actual mechanisms that you would use for how you would implement the different patterns. So in the SPMD, you write the same program. In loop parallelism, you have your program. You might annotate sort of some pragmas that tell you how to parallelize your computation. In the master worker model, you might have sort of a master that's going to create threads, and you actually know the work. You might sort of have a very good idea of what is the kind of work you're going to do in each thread. In the fork join model, you have more dynamism. So you might create threads on the fly. And you apply these sort of based on sort of appeal or what is more suited in terms of implementation to each of the different patterns for how you actually organize your data. So in the task parallelism model, this is where you have a world of threads that you know you're going to calculate or that you're going to use for your computation. And really, you can use largely any one of these models. So I used a ranking system where 4 stars is really good, 1 star is sort of bad, or no star means not well suited.
Actually, in cell, because the inherent master there, sometimes master worker might get a little bit of a biasing than this one. Because
right. So
you don't have to pay a cost of having master, otherwise master is not doing it.
Right. Although you could use the cell master to do regular computation as well, but yes. So in the divide and conquer model, it might be especially well suited for fork and join because you're creating all these recursive subproblems. They might be heterogeneous in the nature of the computation that you do. You might have more problems created dynamically. Fork join really works well for that. And in fact, the subproblem structure that I showed, the graph of sort of division and then merging, works really well with the fork join model. In the recursive, in a geometric decomposition, this is essentially your lab 1 exercise and the things we went over yesterday in the recitation. You're taking data and you're partitioning over multiple processors to actually compute in parallel. So this could be SPMD implementation, or it could be a loop parallelism implementation, which we didn't do. Less suitable master worker and fork join, often because the geometric decomposition applies some distribution to the data, which has static properties that you can exploit in various ways. So you don't need to pay the overhead of master worker or fork join. Recursive data structures sort of have very specific models that you can run with. Largely, master worker is a decent implementation choice. SPMD is another. And you're going to hear more about sort of the pipeline mechanism in the next talk, so I'm not going to talk about that very much. event-based coordination, largely dynamic, so fork join works really well. So one.
Seems if you're buffering, then you could do OK master worker with pipelining.
Yeah. So next slide.
Okay. Yeah.
So these choices or these trade-offs aren't really orthogonal. You can actually combine them in different ways. And in a lot of applications, what you might find is that the different patterns compose hierarchically. And you actually want that in various ways for various reasons. So in the MPEG example, we had tasks here within each task, identified some pipeline stages. Here I have some data parallelism, so I can apply the loop pattern here. And what I want to do is actually, in my computation, sort of express these different mechanisms so I can understand sort of different trade-offs. And for really large applications, there might be different patterns that are well suited for the actual computation that I'm doing. So I can combine things like pipelining with task-based mechanism or data parallelism to actually get really good performance speedups. And one of the things that might strike you is, well, heck, this is a whole lot of work that I have to do to actually get my code in the right way so that I can actually take advantage of my parallel architecture. I have to conceptually think about the question in the right way. I have to maybe restructure my computation in different ways to actually exploit parallelism. Data distribution is really hard. I have to get that right. Synchronization issues might be a problem. How much buffering do I need to do between different tasks? So the thing you're going to hear about in the next talk is, well, what if these things really fall out naturally from the way you actually write the program? And if that if the way you actually write your program matches really well with the intuitive, sort of natural conceptualization of the problem. And so I'll leave Bill to talk about that. And I'm going to stop here. Any questions?
We can take in some questions and then have a break.
Yeah.
You talked about fork and join. When you have a parent thread that spawns off two child threads, how do you keep your parent thread from using up an SPE?
So you have a fork join where you have
Most of the time, parent thread might be in a PPE. Mm-hmm. And so if you just do fork join, you might not really use PP unless you can, you have some time and you let it do some other task and come back.
So, like for our purposes, we shouldn't spawn off new threads from the SPs?
So most of the threads that are spawned off are done by the PPE. So you have these, in fact, a good walkthrough in recitation yesterday, you have the PPE essentially sends messages to the SPEs that says, create these threads and start running them. Here's the data for them. And then these threads run on the SPEs and they just do local computation. And then they send messages back to the PPE that says we're done. So that's essentially implements the join mechanism.
On the other hand, if you are doing something like master-slave way, and then SPE can send a message and deliver another job into the PP who keeps the master. So if SPEs realize there's some more computation, it can say, okay, look, put this into your queue and keep sending messages, and so the master can look at that and update the queue. So it's not only master who has to fork off, but the slaves also, the SPEs can send information back. So you can think about things like something like divide and conquer done that way. There are I guess 6 SPs running, and you first get some things in there, and then each SP says suddenly if you want to divide, it will take one task and run that and send the other one to the master. Say here, say that somebody finish it and send me here's my ID, send me the message when it's done. And so you go to that end and wait. So you can assume you can do something like that. So it's almost master slave, but there's coordination in there. The trouble with normally fork join is if you create too many threads, you are in like a thread hell because there are too many things to run. And I don't know, you can't multi-thread SPs.
No.
So you can't even do that because there's some physical limitation. You can't create 1,000 threads and assume somebody will do it. If you do want to create 1,000 threads, you have to run another master-slave thing yourself to time multiplex those 1,000 threads on top of your SPEs, and that's going to be a lot. You have to include both levels.
So yeah, context switching on SPEs is very expensive. So if you create more, so on the PlayStation 3s, you have 6 SPEs available to you. So if you have a lot more than 6 threads that you've created, essentially each one runs to completion. And then you swap that out and you bring in, well, that terminates, you deallocate it from the SPE and you bring in a new thread. If you actually want to do more thread-like with dynamic load balancing on the SPEs, it's not well suited for that, just because the cost is very high.
The model that we there is master slave. The PP basically deals the master part, it will run most of the sequential code, and then when there's parallel things, it will send, it will keep a queue, and probably the work queue model type thing, send stuff into SPE and feed that. And even like, yeah, so work queue type models can really fit in there.
Yeah, and the SPMD model might not work really well because you have this heterogeneity in the actual hardware, right? So if I'm taking the same program running on the SPE versus the PPE, that code might not be, so I essentially have to specialize the code, and that starts to deviate away from SPMD model.
In some sense, I think most of the code you write for cell will probably master work. And if you're trying to do something other than, you should think hard why that's the case.
You can do fork join, but you know it's.
No, then you, I mean, you can't, because you don't have virtualization. If you fork too much, where are you going to put those?
Right. Bounded fork.
Yeah, but in that sense, if you do fork too much, if you keep a work queue on the master,
right,
you can fork things. You can do a virtual fork and send a work to the master and say, hey, I forked something. Here's the work. I mean, the key thing is do the simplest thing. I mean, you guys have 2 weeks left, and if you try to do anything complicated, you might end up with a big mess that's undebuggable. Just do the simple thing. And I think that's, parallelism is hard. Debugging parallel code is even harder. So instead of trying to push the limits on complexity of messages going all over the world and then 3 different types of parallelism all trying to compete in there, just do the simple thing. Just get a simple thing working. First get the sequential code working and keep adding more and more slowly, and then make sure that each level it works. The problem with parallelism is because things are non-determinism, some bugs that might show up later might be hard to solve. So the design actually really matters in this one. Another thing I think, especially for doing demos and stuff, would be nice would be to have a knob that basically you can tune. So you can say, okay, no SPs, everything running in PPE, 1 SP, 2 SP, 3 SP, so you can actually see, hopefully in your code, how things improve. That would be really cool, especially for the demo part.
Okay. Any other questions? All right, we'll take a brief break and do the quizzes in the meantime.
And for this quiz, there's one thing that didn't mention. So you have multiple cores. You can write either one gigantic core or 1,000 small cores. And we didn't say anything about performance of each core. So one extreme assumption is no matter what size of the core, it all has the same performance. But that would be hard to justify. So you have to make some kind of assumption saying how the core size relates to performance, and then it's up to you. I mean, these things are, there's no nice simple equation saying it's proportional to the area versus whatever, because there's a lot of things go into that. But you can make some assumption in there and just write one sentence saying this is my assumption. This is how core's performance, and then you can just put some math and prove that. And of course, if you come up with a very complex non-linear assumption about cache sizes and stuff like that, things become very hard, but you don't have to.